Hello, my name is Murray Estes. This is a presentation of my analysis on Tor Browser, we'll get into that in a minute, what it is. This is a quick overview of what I'll be covering today. First off, we need to know what is the purpose of Tor Browser. What does it do? Tor Browser is an attempt to achieve a low latency anonymous browsing. This is similar to other programs such as the Anonymizer, Crowds, and Freedom. One of the goals is to circumvent state-level censorship, which brings into question some legal issues which I'll talk about in more detail later. This is also to protect individuals such as journalists, missionaries, what have you, from hostile populations and areas where, again, these speech is curtailed and generally prohibited. And in general, it is intended to mask the geographic location of a sender and his recipient. Now, what do I mean when I say low latency? I just mean that the method creating this anonymity has little to no impact on the time it takes to send and receive data. And the opposite of this is known as high latency. Low latency is better suited for applications that involve instant messaging, email correspondence, and general web browsing. And this is very possible in theory. However, it has been shown to be difficult to accomplish in practice, and in some cases, it simply cannot be done. Peer-to-peer connections such as BitTorrent cannot be done using Tor Browser, at least. Now, how does this protect people from hostile populations? You can gain identity of the sender and the recipient through their IP addresses. And IP addresses can indicate the geographic location of the individual. Tor Browser attempts to make it unclear as to whether packets are being sent and received through a given server or node, or actually have originated from that IP address. And some nodes within the Tor network can actually spoof IP addresses. Not all, but some can. And in general, in theory, the packets cannot be traced back to the sender, which in turn protects the user from local hostiles. Again, this is a maybe, because there are ways where you can be identified. I'll get into that later. Now we've talked about the general purpose of what Tor Browser does. Now we need to know how exactly, or at least the high-level details of how Tor Browser works. There are two main components, one of which I've already mentioned, the Tor network, as well as the actual browser itself. The network consists of three components itself: the circuits, the nodes, and hidden services. We'll talking more about the circuits and nodes as we go along. Hidden services, you just need to know that they're there. And then the browser itself is a very heavily modified version of Mozilla Firefox. And in fact, some of the Firefox developers actually helped make some of the modifications to the browser. So, going into more deep depth for the Tor network, the network consists of components known as nodes. They are also known as onion routers. These are operated by volunteers across the globe. And some, but not all, are capable of spoofing addresses, as I mentioned earlier. And some of these nodes are special nodes, depending on your application within the circuit. These include your guard nodes, your exit nodes, and then there's an authority node. The guard nodes are a defense mechanism against particular attacks, in particular the man-in-the-middle attack, which I'll get into later. The guard node is a primary defense against that. Exit nodes are the nodes where you basically jump out of your circuit to achieve either the web service or the hidden service that you are requested access to. And then the authority node, there's very few of the nodes in existence, and all the nodes combined form what's known as a consensus. And this consensus contains information about the Tor network as a whole, what all nodes are there, what nodes are connected, how I'll get into a little more detail about their functionality later as well. In fact, I'm actually into it now because I want to talk about circuits now. Circuits are generated by an algorithm, and the nodes added to the circuits or removed from the circuits must be approved through the consensus by the authority nodes. And the multiple circuits can be created. And there are backups in case at least one of the circuits becomes compromised. And there are different circuits for different services there. The circuits to access hidden services, these are also known as internal circuits, by the way. And you have access to web services. And you're going to use the exit nodes to go to the web services, by the way. And this is all this information is maintained by the authority nodes through what's, as I've said before, the consensus. It contains information about the nodes, the state of the network as a whole, and other relevant information. And then the browser is based on Mozilla Firefox. This was chosen because of its sandbox environment and it is open source. Now there are some key differences in the Tor browser and the modified version. One is that it enforces a do not track flag. Now, this do not track flag exists in the out-of-the-box version of Firefox, but protocols used by the normal Firefox do not enforce this. And so this becomes enforced with Tor Browser's version. And then they also disable the use of cookies because cookies can be used to identify you. And then the browser also spoofs a lot of your information about the browser and your system. So just to prevent you from being identified. Now we've gone into purpose and we've gone through how it works to a very simple degree. Now we need to go into some of the known problems with Tor Browser, or at least how it functions problems. How about that? And there's two primary vulnerabilities here that come into play. One is the man-in-the-middle attack, which I mentioned earlier. The main defense against those are the guard nodes. The other is a thing known as fingerprinting, which is based off of two things: your browser attributes and an analysis of your request traffic request. I'll learn to speak one day. All right, man-in-the-middle attacks. Now, I should mention what they are first before actually going into this slide. Man-in-the-middle attack is where you have your adversary. So you have you and you have your sender on opposite ends of your network. The man in the middle is going to appear somewhere in the middle along your route, and he's going to look at your data. So try to use that to identify what's being sent and other various information. In the case for Tor Browser, in most cases, the adversary is simply trying to identify where you're sending from and where you're sending to, and maybe even more importantly, who you are. I'll get into the reason why that is when I talk about the legal issues, because most adversaries in regards to Tor Browser are looking to restrict your ability to speak and communicate and what have you. Anyway, for the man-in-the-middle attack in regarding to Tor Browser, the adversary is going to attempt to capture data sent through HTTP authentication and TLS handshakes. You cannot get away from these. Every time you send a request to a new page, you do both an HTTP authentication as well as a TLS handshake. This occurs every time. And the data contained within these authentication protocols and the handshake protocols contains identifying information. It contains your IP address and other metadata about your browser system. And Tor Browser defends against this in part with the guard node on top of the guard nodes. More locally, information about your system is isolated. And if it cannot isolate by this I mean it cannot be accessed by external actors through the attempts to hide it from the HTTP authentication protocol and the TLS handshakes. And what information cannot be hidden is spoofed. This is just a fancy word for being made falsifying, if you will. And of course, as I mentioned earlier, the do not track flag becomes enforced. Fingerprinting. This is kind of like in forensics. You've seen the movies or the TV shows where the crime scene, you have the crime scene, they've dust all the stuff and they find fingerprints. Well, this is the digital version of that. And so we have the browser attribute, and so we can gain information about the sender through attributes about the sender's browser, such as their request behavior, in particular through the headers, pipelines, orders, and even filters that are being used, such as adblock, can give away who you are. And your DOM data, which is information about your machine. And JavaScript in particular is extremely effective at obtaining this information. It can even obtain the exact information about the very CPU you're using, your video card, and most dangerous to Tor browser, your time zone, which is your locality. And then also a list of plugins can also uniquely identify who you are on the internet. And plugins have some other vulnerabilities as well, because plugins have a strong tendency to ignore proxy protocols. And Tor browser and some of the modifications that Tor developers use for their browser involves a lot of proxy information, a lot of proxies to circumvent state protocols. And plugins can also have very unusual cookie formats that are not easily recognized, and so they're not easily cleared from your system. And as I just said, the list of the plugins you use is enough to can be enough to uniquely identify who you are, or if it's not, it can severely narrow down the number of possibilities that, hey, you're the guy that I'm looking for. And then the other approach is through traffic analysis, which is just the pattern for accessing particular sites. And for this particular approach for fingerprinting, they're actually trying to determine where your card node is. But because of how Tor network works, this becomes a very expensive process, and developers at least believe this is very unlikely to fail. Although in their code they do include some lightweight protections that I'm not really going to go into. But the browser attributes is where you're most vulnerable in regards to your anonymity. And this is where most of their effort has gone for defense. And in regards to fingerprinting, almost all of the information cannot be hidden. And so instead it gets spoofed. It gets made false. And in regards to your plugins, no plugins. They're all disabled because, as I said before, your list of plugins can identify who you are. Cookies are also disabled because cookies are problematic in that they ignore proxy protocols, and that their formats are very difficult to clear from memory. And in regards to memory, there's also an attempt to keep your memory cache as clear as possible. So we've talked about the known vulnerabilities of Tor, as well as some of their defenses. Now I need to mention the legal issues surrounding Tor. In many states across the world, they have attempts to curtail the freedoms of speech, the freedoms of press, what have you. And Tor browser is one of the tools used to circumvent this. States that typically restrict speech have also restricted the use of anonymous browsing tools, including Tor browser. And in some states, if I remember correctly, Iran is one of the examples used for this. Simply being suspected of using anonymous software like Tor is enough to have you arrested. And this is why, for users of Tor browser, maintaining the anonymity of both the user and the node owners is essential. Because not only would the user themselves could be held legally viable, the owners of the respective nodes within the Tor network can also be held liable. And so, Who exactly is crazy enough to risk being arrested for using the software? Well, anyone who needs to circumvent censorship, such as journalists. Again, remember, all these places that restrict freedom of speech also restrict freedom of the press, especially when this press is extremely critical of the government. Missionaries can also fall in this category because in a lot of these areas, there's also extreme restrictions on religious practices, and missionaries are particularly vulnerable. Missionaries also fall in the second group I mentioned of people who want to avoid hostile locals. Military service members, foreign militaries in particular, also benefit from this capability, as well as revolutionaries. And in general, anyone who just does not want to be tracked benefits from the use of Tor Browser. Now we've got that little bump in the road out of the way. Now we'll go into the fun part. My analysis of Tor Browser. And I'm first going to cover just the tool I used. I intended to use more than one, but I only had time to use one. And just the general methodology behind what I did. I used a static analysis tool known as Flaw Finder. And like I said, I intended to use a second one as well. I wanted to run the two different tools and compare the results to help narrow down where I actually needed to look, instead of just going through all the results of one. And then I did a manual review of the code, starting with what I got with the hits, if you will, from the static tool Flaw Finder. And then I looked at the surrounding code as well, just to make sure that code was sound. And now, why did I use Flaw Finder? Flaw Finder is very simple. And that's both its strength and the downside as well. It runs very quick because of its simplicity. It runs very quickly. You can analyze tens of thousands of lines in just a few seconds. And what it does is it takes all the function calls within the code and compares it to a list of known functions that have been problematic in the past. And it tries to explain why that function is a vulnerable function, and where possible, it suggests alternatives. If it can't suggest an alternative solution to your code, it tells you what you need to check in order for it to not be as vulnerable. However, again, because of its simplicity, it does not catch or capture all of the vulnerabilities. For example, problems with user authentication will not be captured by Flaw Finder, and any code that could be removed due to the compiler cutting it out for optimization purposes. Again, Flaw Finder will not identify that. And actually, there's a couple places that get pointed out here where that actually would happen, where the code would get cut out by the compiler, and it gets flagged for a different reason. Now we get to look at what I found. This is a general analysis, the summary of the analysis generated by Flaw Finder. You can see there's a little over 3,000 hits out of all those lines of code. And there were 17 hits at the most critical severity level. There were none at the least, actually, which is 0, but there were over 1,000 at the next to least. And almost all of that 1,000 involves string length function, because string length function only stops counting when it gets to a null. And if you try to use a non-null terminated string, then it will read over your buffer and read outside of your buffer, and that is always problematic. And here's some other notes. At severity level 2, about half the hits were involving hits on static arrays, which is warning about the risk of overflow. You have any calling function you need to check, buffer sizes, whenever they're using it, both for reading and writing. And also the other half is memory copy, which doesn't check for your buffer size of your input or output. And it's also an overflow risk. And when I say the system from here on out, I'm referring both to the local system as well as any connected circuits. I include every single hits at level 5 and 4 because these are considered to be the most catastrophic potential risks. Once you get to 3 and 2, I try not to include repetitives on 3, beats on 3, and then on 2, I just don't. I don't include all those there again. I try to cut off a repetition, redundancy of saying the same thing over and over again. Because that's the case a lot of times with 2 and 1. I would be saying the same thing more or less every time for 1. All the ones would be the exact same thing, and I'm not repeating myself 1,090 times. I've already said what I need to say about those. 2, there's a few issues with the 2 though that we'll discuss in more detail when I get to it. I guess I should also mention that I should repeat that there were no hits at level 0. The threat level 1 is the lowest threat. Our first hit is in config.c file with the use of chmod. What this function does is it grants read and write privileges to a particular user or group. And the problems with that function are several. Should be kind of obvious, especially if the calling function has set UID access. And in this particular case, if the permission is not granted, an error message is generated. And the main thing Flaw Finder warns about here is about an adversary possibly moving the directory or file, which would cause a race condition. And this is really the same thing, except the previous file was actually correct. It's actually granting the privileges to a directory. This is correct, granting them to a specific file. Again, if the level is not given, error. And Flaw Finder makes the same warning. And there's the other. In connection.c, we move on to chown, which this function grants ownership of files and sockets in this case. In this case, it's a socket. And this could be used to grant, and the way this is called, it could be potentially used to grant ownership of a socket to an adversary, which it grants them access to the system, especially if they are able to alter any arguments. In OpenBSD, Malik Linux, use of relink to use the configuration file, and if the file can be altered, then the adversary can affect the system. And the configuration file is there. It's there, ready to be altered. In control.c, again, we're going back to chmod. And it's used to make a file readable by a particular group. But in this case, the function calling chmod is also the function creating the file. So really, this is only a vulnerability if the adversaries are already in the group. And this could be the case, as I mentioned before, the man in the middle. This could be one of the cases where man in the middle could occur, code-wise. HS service C, chmod, this is the exact same scenario as before. It's actually the exact same function, just throw it in this one, throw it in this file. So the same vulnerability exists here as well. In sandbox.c, we have several lines where it's flagged for chmod or chown. But these are actually contained within strings to be used as a parameter for a function. The function is checking to see if they're there. And no vulnerability with these lines. The next three I'm mentioning are all for debugging. So the end user should not have access to these functions to begin with. They're there for debugging purposes, so the developers don't have to rewrite the files every time. And again, chmod, we're granting permission to a particular group. And as before, if the adversary can alter the file, then the adversary can get into the system. Same thing. Okay, CF5, I'm repeating myself. And I think the same, yes, it's the same function, way further down the code. Again, ch is using chmod to grant permission for a particular group to a directory. And again, if the adversary can alter it in any way, then the adversary can gain further access to the system. And so the last of these testing functions, again, not really vulnerability because they're only in use for debugging. They're only used debugging by the developers. This time it's use of chowned, which sets the ownership of a directory. And again, if the adversary can access the directory as an owner, then the adversary can affect the system. And now we get out of the level 5 into the next level down, which is 4, with rend passphrase.c. The use of the function getPass, which is deprecated. This function, it really should not be used. And then I don't remember the other function that FaultFinder recommended, but it's irrelevant in this case because this function actually isn't used. Remember when I said that FaultFinder doesn't consider code, doesn't note code that gets cut out? This is that function I was telling you about, that it calls for a different reason, but this code actually gets cut out during compilation because of a macro, in particular the f0 this and diff type macro that gets cut out of the exact, it gets cut out of the binary, so it's not even there. In timeout debug.h, we have fprintf. For the record, just about every printf function makes its appearance here in my little analysis. And this is used to print an error message to the standard error. And if the adversary can alter the parameters, which are file, line, and function, and the adversary can affect the system, maybe. But I didn't see a way where this could happen. So there's that. Timeout.c, we're back at fprintf. And this one prints the variable number of arguments to a supplied stream. And again, if the adversary can alter either the arguments or the stream, then the adversary can exploit something and can affect the system. The more specific wording from FaultFinder is exploit the system. But effect is about the same. But like before, I really didn't see a way where this would happen. But then again, maybe I overlooked something. Hard to discount that. Here's another test function which really only gets called during debugging. But this is printf, and this is used to just print a bunch of statements pertaining to a series of tests. Particular statements do not contain formatted input, and printf always prints the standard out. So this really is a vulnerability because there's nothing to exploit here. And Tor API.c, the use of S in printf. Well, these two end up being identical, line 42 and line 112, but the exact same problem. S in printf, which prints a limited number of bytes to a string. So that's a plus. We have a limit on our buffer read. The question is our in and out buffers greater than or equal to the size of, actually it really just needs to be greater than the size of the data being read in. And in this case, they're both greater. And they're both also the same, and both the data buffer sizes are the same. So this really isn't a vulnerability in this case, and the data is not formatted. Then we get to this one, fprintf, it's being called within a wrapper function, and this wrapper function handles the known vulnerabilities of printf. Compiler again, we're talking about printf, and in this case, this is just a parameter in a function that checks for the existence of printf in the system. It's checking to see what kind of compiler has been used and whether it's a GNU system or another type. And then in winlib.c, we have tcscat, which is a concatenation function. And this is one of the more iffy code pieces of code because this function, tcscat, does not check your input size against the remaining buffer space. So overflow can occur if you're not checking in this function. And the function that calls this does not explicitly check the size of the remaining buffer. So in theory, a buffer overflow can occur within this file. I didn't include the exact within that line, the function that contains that line. I can include the exact function. I did that for security reasons. But function does not explicitly check it. So buffer overflow theoretically can be, even though logically it shouldn't happen. But the thing about logic is there's always that case you overlook that defies all the logic you're looking at, what you're thinking of, and then all of a sudden you have a buffer overflow. Why? Well, it's because you didn't check. And that's what's going on here. And if you remember, this is the last of my, no, it's not, it may be the last of my level 4s. Anyway, in sandbox.c, we have the function access function, which simply tries to access a file along a path. And in this case, access is an argument to a function, but it is trying to access something. And so if in any way that the path that access is calling can be altered, then the adversary can access the system once whatever access is calling is called. Once that happens, then the adversary can gain some effect on the system. Then in printf.c, it's probably the worst of the printf functions, vs in printf. And I say that simply because this is the one that doesn't null terminate anything. It prints a variable list of items to a string, and it does not end the string with a null, which can be problematic. But the function that calls vsn printf is a wrapper function, and it's taking into consideration the vulnerabilities of this function, so it's being used safely whenever it's called elsewhere in the program. And here's a test function that appears only debugging. It's to use the scanf, string scanf. Okay. Yeah, but it's an argument for a function, and the calling of the function it's being passed into is looking to see if a generic wrapper works properly. That's the only reason why it's ever called. And Tor runner.c, this is the last of my level 4s. Okay. We have the execv function, which calls an external file for execution. If any argument to this function can be altered in any way, then the adversary gains control of the system. That's just how it is. Now we're at level 3. Not so serious. I'm going to start omitting some of the hits. There's not 26 here, but I think I'll have like 9 or 10 slides for getting over. Anyway, the main Tor main.c and main loop as well is the same thing. The get environment variable function. Environment variables are generally not trustworthy, simply because they can easily be manipulated if adversary can spoof any data about them. Anyway, and if that can happen, then your adversary can affect your system even further. Now in bench.c, remember this is a test function, so it shouldn't be called normally. But the use of random here is flagged because random should not be used in cryptographic contexts. In this case, it's not being used in a cryptographic context, so it's not a vulnerability. With lib.c, we have the use of load library. And if the path fed to this function can be altered, then the adversary can wreak havoc on the system by altering your library file. Fun. And this function occurred like 7 times. It was in the same file. This function was flagged like 7 times. Because how many times it appears? 6 or 7 times. And in the initialize critical section, what this does is it tells the system, hey, this function is in this process is entering a critical section. It needs to be locked. And this function gets flagged by flaw finder. This particular variant of the function gets flagged by flaw finder because it can throw an exception whenever the system is running low on memory. It instead recommends the use of initialize critical section and spin. I don't remember the exact difference between those two. That's in my operating system class. I'm taking how it just changed. Yeah. Level 2, I skip a lot of hits on this one. There's like 2,000 hits, and I think I only cover like 40 of them. Config.c, we're complaining about the use of A to I. This is because whenever the input to A to I is greater than the upper bound of the integer type, it rolls over into negative values. And likewise, if it is a negative value fed into A2I, if it gets below the lower bound, then it rolls over into the upper end. And your calling functions need to check this. And the calling function in this case does. This isn't necessarily a vulnerability, it's more of just making sure you have the desired behavior. Meme copy, this one occurs. This one happens a lot, and you want to hear me say this. Something the same general idea is going to be a boring refrain. But to use a meme copy, you have an input buffer, an output buffer, and a number of bytes being copied from the output to input. All of those have to agree in some shape or form, whether the number being read is smaller than the buffer sizes, or one buffer is much larger than the other and you're just copying all of the smaller to the larger, or you're copying a fragment of the larger, which can be done, to the smaller. In this case, the size of the buffers are the same. This is actually going to be a recurring thing, it turns out. The buffer sizes are the same, and they're both greater than the size of the amount of data being copied. So this is not a vulnerable. So in this case, it's fine, it's safe. The other big complaint was the use of static arrays, in particular static character arrays. In this case, as long as the output from the version of the function get version does not exceed the buffer size, then that's the only function that calls this buffer. The buffer flagged anyway, I didn't write down the exact buffer. Then the risk of overflow is not present. And for the record, the output of get version is always less than the buffer size. Good margin too. And then two more arrays. One is key, the other is output. And as long as the size of one is less than the size of the other, then there's not a vulnerability in the functions that call them. And they're always called together. Almost always called together. The meme copy. As long as that. As long as As long as Tor CFG argc times size of carstar is less than the size of argv, then there's not a vulnerability. Otherwise, there is. I think if I have time to fully trace that and make sure that's the case. Lots of digging in code was scattered all over the place. But, yeah. If that's the case, then that's it. Likewise here, if Tor and circ configuration argc owned times size of carstar, if that is less than the size of argv Tor config argc, then there's not a vulnerability. If that's not the case, there is. And this one, oh yay, I know this one. I know this one. This one, the calling function never checks your buffer, never checks the buffer sizes. So overflow is very possible. Unless, of course, the function calling this function does the check. So if the function calling this function checks, then you're fine. Otherwise, problem. Potentially. And this is a repeat, just because it is a potentially severe vulnerability caused by buffer overflow. As long as the size of curve 255.19 public key type is less than the size of what's at the address of state pub key B, then there is no vulnerability. Here, and same file, onion and tor.c, and again, name copy. As long as curve 255.19 public length is less than the size of data of structure S public key Y public key, then there's no vulnerability. S is one of those hidden structures that they created. I couldn't really, it's actually fine right above it, but I don't remember all the details off the top of my head. I didn't think to write them down. Onion tab.c. As long as those two functions check the buffer size, he complained about buffer size before this being used, and there's not a vulnerability. And from what I saw, in almost all cases, they did check the buffers at some point. Except for most of the time they did. I've pointed out 2 of the times we did so far, though. Unless they did before calling that function, like I said. Likewise here, they check the buffer, then there's no vulnerability. I didn't, this is why I was running out of time trying to do all this. Oh, yeah. These functions have to be checked. And then that function, if that function checks the size, then checks it correctly, of course. You have to check it correctly as well. And there's not a vulnerability. And that function, that file, QST, this is primary structure definition. This occurs a few places, quite a few places actually. And as long as the functions that use this buffer check the size prior to using, there's not a vulnerability. Of course, when I say check, I am assuming you're taking correct action when the check fails. So, circuit build.c, another array. As long as those two functions, onion skin client handshake and circuit initialize cpath crypto, check the buffers before using them, then there's not a vulnerability. And then as long as, again, another array, as long as those 3 functions check, then there's not a vulnerability. Another array, 2 more functions to check. Yeah. Ooh, this function. This one's fun. The use of the function open. The file should, in general, when you use the open function, you should check the file before using it, because an adversary could alter the file, which could lead to damage to your system. But in this case, the function that's being opened, the file that's being opened is being created by the function calling it, by the function opening it. And so in theory, it should be safe. And like as I've alluded to, there are way more hits than I've listed. And almost all of the ones I did not include are harmless. I only listed those that are problematic or were just some random examples of things that Flaw Finder tagged just so you see what it did. And because many functions are imported from other files, the way the files are organized kind of makes them difficult to properly trace every single hit. I traced as many as I could in the time given, but I didn't quite get through all of them. And since I relied very heavily on Flaw Finder to find problems in the code, there are other vulnerabilities. There could be other vulnerabilities that I missed that are just caused by poor coding practices. I didn't see that many of those. A couple maybe, but I pointed them out. I would have said something if I did. What I did. And we've gone through the results of my analysis, and now we just go to an overall summary. As I said before, Tor Browser attempts to permit anonymous browsing without significantly affecting response times of the application. Tor is divided into two parts, the Tor network and the web browser itself. It has vulnerabilities, man-in-the-middle attack, and fingerprinting. And I've discussed some of the ways that Tor Browser defends against these. My limited analysis just shows some places in code that could be exploited, especially in conjunction with some of these known vulnerabilities. And despite the vulnerabilities and legal risks, though, Tor Browser can still be an effective tool to communicate in all states and prevent state censorship where such is in place. These are a list of the references that I have used throughout this project. And this concludes my presentation. I thank you for sitting here listening to my horrible way of speaking. I will learn how to speak one day. It just won't be today. I thank you, and I hope you have a wonderful day.